Welcome to this Dragonfly 4 training video. In this tutorial, we're going to be looking at the bone analysis extension. This will give you an introduction to some of the basic features of analyzing microarchitecture of bones, both inspecting cortical structure and trabecular structure, and some global measurements that can be made on those attributes. The data set we've selected for this experiment and tutorial is a micro CT scan of a bird humerus. We'll be looking at this data set and we can see that it's a high resolution scan that has quite a bit of detail. Now, what I'll get started by doing is adjusting the windowing and leveling of my particular data set so that I can have a good view. Now, what I'll do here is I can adjust the window and level, but in addition to that, I can, with the data set selected, I can come over here and choose from different presets that will affect different lighting models that can help us get a good or decent rendering of our data set. So we have a 3D rendering of the bone, and I think that's going to be fine for now. Now, what we'd like to do is we're going to go through a process of segmenting the bone, but before we do it, we need to make a few observations about the bone. One of the things we'll be doing is classifying the bone into cortical and trabecular, and that's going to depend a little bit upon the dimensions of our bone. If I use the annotate panel to make measurements, then we can see that the cortical bone has some thickness, so in some places it may be around 800 microns. If we look at the trabecular bone, then we might see that it has different thicknesses in different places, so it may be on the order of 150 microns. Some places it may be a little bigger, some places a little bit smaller. Now we'll refer back to some of those measurements later. I can hide all of these measurements, or I can select them all and select them all with a shift to select and just delete them from my workspace. Now, one of the other things we need to look at in order to do the proper cortical and trabecular separation and segmentation is there could be gaps in the cortical bone. So as we're scrolling through, we see there's a gap right there, and we will have to apply a parameter to help us close any of those gaps. So it could be good early on to make a measurement and see what those gaps look like. So they may be on the order of a couple hundred microns, so maybe a little less than 300 microns, and we can round up for safety later on. So when we look at this bone, one of the things that grab your attention is, unlike other long bones or unlike long bones from other animals, there is this particular structure here. And what we see is there is a very large gap in the cortical bone. And that's there evolutionarily intended. In birds, there is this air sac that's part of the humerus, and that's part of the bird's, that's part of the avian respiratory system. We're going to do, during our segmentation, we'll have a closer look at that, and we'll apply an artificial cap that will help us get a proper segmentation of cortical and trabecular. If you want to have a look at this, you'll note that right now when I rotate, the center of rotation is the center of the bone. And if I want to have a closer look at that, then I can select the 2D view and I can turn on this state, which is the pivot point, which allows me to click in the 2D view, and if we turn on pivot point, and then I can just drag that down. And now when I go back to the 3D view, it's now pivoting about that point. So you can see that gap in the cortical bone structure. Now, we will be doing some segmentation. I want to show you a couple of features of segmentation in Dragonfly. On the Segment tab, there are a number of panels, including the ROI tools. You can always create a new region of interest for labeling different parts of your data set. So in this case, I'm just going to create a new region of interest. It's just going to be called ROI1. And I want to do this to demonstrate one of the features for automatic segmentation. And what I'm doing here is I'm just turning on a 3D paintbrush in the shape of a cube, and I can reposition the paintbrush with my mouse, and if I hold down the control key and I drag the mouse wheel, I can change the size of a brush. But all I've done here is, when I click the mouse, is I've painted a 3D region. And the reason I've done this is I want to point out that any time in Dragonfly that you establish a region of interest, one of the things you can do is select that region of interest, and on the ROI Tools panel, ask Dragonfly to perform an automatic segmentation, that is an auto thresholding inside the painted area. And what we see here, if we double click and make it go full screen, we see here that it has taken this green region of interest and it has split it into the background or dark pixels and the foreground are bright pixels. So this Otsu thresholding, or automatic thresholding, is a decent way of performing an automatic binary segmentation. Well, what I can do is I can delete these two regions of interest just by selecting them both and then doing a delete. And I can repeat this procedure, but instead what I'll do is I'll select this region of interest, I'll clear everything, and then I'll click invert. And I'm going to go ahead and turn off 3D rendering for now. So now with everything selected, I can do a split at Otsu, and it will evaluate Otsu over the threshold of the entire image, and it will give me two new regions of interest, one for all of the hard tissue, which is bright, and then one for all of the darker pixels, which could be soft tissue or could be air, anything that's not bony tissue. So this is one of many different tools in Dragonfly for segmentation. So at this point, we're just performing a binary segmentation to label what is bone and what is not bone. And this is just a simple way that doesn't force us to use any user bias, where the user may select one threshold and another user may select a different threshold. Instead, we're letting the Otsu algorithm decide. And so if we look at the yellow region of interest, which I'm going to recolor and make blue for now, then we have all of the bone labeled here. So this is a segmentation of the bird humerus, and that's what I'll name it. Just by clicking on it, I can change the title. Double clicking on it, I can change the title. We don't need these anymore, so I'm going to select them both and then delete. Now, I mentioned earlier that this gap here is going to confound our, or could confound our cortical trabecular segmentation. So because there's a gap here, the Dragonfly algorithm may detect the bone here as cortical because the cortical bone is missing here. What we can do to correct that is we can actually just manually add a false cortical cap. Let me show you how I'm going to do that. First, I'm going to make a copy of the data that we're working on, make a copy of the binary segmentation. Now I'm going to reposition the crosshairs here just by dragging, and I'm going to tip this direction, and I'm going to come over here and tip this direction. And what I'm doing is I'm just repositioning so I can find, I'm repositioning the green plane, which is this view. And as you can see, we're now looking at the opening into that air sac. And so it's this view right here. If I were to take the lower left view, the bottom left view, and plot it, then and do a show data, you can see now that we've positioned it just about at the spot that's, and I can grab it and manually adjust it here if we want. But this allows you to decide and interact and get that that spot where that cap is. So, or where we want to position that cap. So once we've placed it, we can actually use the manual segmentation tools to, it looks like I accidentally tipped it in this other plane. So we'll just make sure that it's tipped back. So I can turn this off for now. What I can do is I can come down here and I can scroll through until I hit the top slice where that cap needs to be. And I can go to segment and use the ROI painter in 2D mode with a round brush with this ROI selected, a round brush, and I can use the control key to change the size of the brush, and now I can just paint in here, and this doesn't have to be too precise. And so now I've put a false cap in. If we go back and look at it from this view, you can see we've made a bit of fake cortical shell bone there. What I'll do is I'll rename this capped. So we have our true bird humerus segmentation, and then we have our capped segmentation. Later we might want to be able to subtract this cap out, so it could be useful to have an ROI that stores just the cap. Well, that's really easy. It's just the difference between this ROI and this ROI. So if I do a control select, I want to do an A minus B, and put it in a new region of interest, which we will call capped, and I'll change the color and make it red. And if we then turn on the visibility, then you can see, well, I'll move this slice out of the way. Then you can see that cap is clearly marked in red. Okay, so now we're going to, so we've done at this point is just set up a binary segmentation of the bone. And if we didn't have that air cap that air sac, this wouldn't be so laborious. We just have to take special precautions because this is missing some of the cortical bone. But you see, that was really easy for us to do. I'm going to reset my views. And what I'm going to do now is, for the first time, I'm going to go over to Tools and choose Bone Analysis. The Bone Analysis extension is divided between two tabs, one for cortical trabecular analysis and measurements, and one for mappings. We're going to save mappings for another tutorial video. But what you see on the cortical trabecular measurements, it's divided into two halves, the top and the bottom. The top is where you can perform a cortical trabecular segmentation. In this case, we're going to take the capped bird humerus, and we want to subdivide that into cortical and trabecular. And there are two different methods that are implemented in Dragonfly 4. There's the Kohler method, which is described by Kohler and colleagues in 2007, and then there's the Bowie method that's described by Bowie and colleagues also in 2007. If you're using either one of these methods, then please be sure to cite these papers when you're writing up your manuscripts. So for this bone, we're just going to choose the Bowie method. And recall earlier on, I looked to see were there any holes on the surface and what was the trabecular thickness. And for this, I'm just going to set Dragonfly to try and fill in any holes on the surface that are 500 microns or smaller. And I'm going to tell it that the trabecular thickness that it should be looking for is on the order of 150 microns. Now, this question of what to measure trabecular thickness, it can be a tricky one, and let me show you in a slide sort of the differences. So this is what a cortical trabecular separation might look like after execution of the Bowie algorithm. And if I tell it to close all holes that are 500 microns or smaller and to treat trabecular thickness as 300 microns, we can get an answer like this. Now, if I do the same thing but I reduce trabecular thickness to 150 microns, then we start to see some differences. So if you look in here, in this area, then you'll see that the orange has a little better labeling of the trabecular bone, and it looks good pretty much all around, whereas the yellow tends to leave a little bit more of this bone labeled as cortical. So we're going to choose 150 microns. Now there are some trade-offs. When we choose 150 microns, it does end up trying to call some of this cortical when maybe we should call it trabecular. So none of these methods is completely perfect all the time, but we get a pretty good result with these parameters. So we're going to go back to Dragonfly. We've got these parameters plugged in, so everything that's smaller than 500 microns on the surface gets filled in. Tell it the expected trabecular thickness is on the order of 150 microns, and tell it to segment. Now this is a multi-step process, so step 1, step 2, you get to step 3 and it actually has several sub-steps. So this is going to take a few minutes to process in order to perform this automatic separation of cortical and trabecular. So at this point we're just going to have to wait for that to compute before we can continue. Alright, the trabecular cortical separation is complete. Let's move this out of the way. What we see are some new objects in our workspace. So that we see 4 new objects, something called cortical area, trabecular area, cortical bone, and trabecular bone. If we take a look, we can see that cortical area, this color doesn't give much highlight. I'll just make it yellow for a moment so you can see. So cortical area is now this area on the outside. Trabecular area is all of the trabecular bone and all the medullary space. Cortical bone is just the cortical bone. It looks very much like the cortical area. There are some differences. You can see cortical area here is a little thicker than what it called cortical bone. And then finally the last one is trabecular bone. Now I'm going to change this color again for better contrast. So we have now, and I'll also scroll down here and I'll increase its 2D opacity. So we see now the results of this segmentation. We can look at it in different views, but we can see that we have a pretty good result of labeling trabecular bone and labeling cortical bone. So there's one of those gaps we talked about that we had to have that 500 micron parameter to make sure gaps like that got closed in the analysis. And so you can see that it does a pretty good job in most places of labeling cortical and trabecular bone. One of the things you can do in Dragonfly is you can use these regions of interest to modulate your on-screen rendering. So if we take our trabecular bone, for example, we can turn on 3D rendering, and now all the trabecular bone is rendered in a orange, and we can make it appear more orange. Whoops, yeah, more orange or less orange. But there are also, and so we could, there are also some features that allow you to adjust I'll double click to make it go full screen. You also have these other sliders, so in addition to making it appear orange or not orange, you could also turn down the intensity of all of the trabecular bone, or conversely, you could turn down the intensity of all the non-trabecular bone. So we can have a rendering like this that sort of lets you see the trabecular bone with a little bit of opacity of the rest of the bone, so you have some context. Or you could turn it down altogether, and now you have just a rendering of the trabecular bone. We can still go back to the micro CT window level settings if we want to further enhance the contrast, or maybe change the gamma mapping to get a good view of our trabecular bone. And of course, you'll explore the different rendering settings of Dragonfly if you want to change the lighting and the shadowing to give you a good rendering. But this is a nice way of seeing where is the trabecular bone, seeing where the struts are and the orientation, simply by taking trabecular bone and telling it to fade away the opacity of everything else so we can hide the cortical bone. So that's one way of looking at it. We could also look at it with the visual plane as we looked at it before. So if I turn on the bottom left visual plane again, I can tell it, actually let me turn it off, and let's say get the trabecular bone colored in 3D, and we'll get the cortical bone colored in blue in 3D. Turn it on, turn on 3D, and what we'll do is make sure that there's some orange and some blue associated with these. And now if I turn on the visual plane, for the bottom left view, one of the things I can tell it to do is I can tell it to take the micro CT scan, I can tell it to take the cortical bone and the trabecular bone and to apply clipping on all of those. If I turn off show data, then now I have a view that, I'll zoom in a little bit, that lets me look at the cortical and trabecular. Let's make sure trabecular has some orange to it. Select the MPR view again. So this is a way of visually inspecting your bone. And so it gives you a nice option. I'll turn this up a little bit and turn this up some. Gives you a nice option for seeing in 3D, so you can see where the trabecular and cortical bone is labeled, and we can tip this and look at it in different orientations. But it gives us a good view of what the segmentation looks like in 3D to complement our 2D views. So that's quite useful, but we'll go ahead and turn this off. So at this point, we have our cortical and trabecular separations. We can use that for visualization, but more importantly, we'd like to use it for quantification. So recall in the bone analysis tab that the top half is the cortical trabecular separation, and the bottom half are measurements we can make. Now, the measurements are going to use as inputs what we've labeled as cortical area and trabecular area, and then the binary segmentation of the bone. Now, I did say that we might want to take our bird humerus and subtract away the cap. We could just tell it to use this. Or if you wanted to, you could use a difference operation again just to remove the cap from that last step. So just want to point that out as an option. We see here that what it's calling cortical bone has this false cap. I can always choose cortical bone and choose the cap with a control select, and I can do an A minus B operation and put the result into the cortical bone. So if we take, let's see, I'll just rename this one cort so it's easy to see. So I'll take cortical bone and capped, and now I will put the result in cort, do an A minus B. And if we are looking at cortical bone, you can see that it has now had that little cap subtracted out. Let's turn it back on. So when doing these analyses, it has to know where the cortical area is, where the trabecular area is, and then the cortical plus trabecular bone, which could be could be now the bird humerus. We'll use that as input. So you'll see here that there are a number of measurements we can make. You have some anisotropy measurements. You have volume fraction. You have cortical and trabecular measurements like cortical thickness and trabecular thickness, periosteal surface, endocortical surface, etc., etc. So there are a number of measurements. These are all global measurements that are going to make a measurement over the entire bone volume and then report out a single scalar value. So some of these are compute intensive. They can take a little while. I'm going to tell it just to compute BVTV and trabecular thickness as an example. And then I will tell it to compute. And then we'll just wait a few minutes for it to make those measurements. And again, we're going to expect two values, one value in the table for BVTV and one value for average trabecular thickness as it's computed over the entire 3D volume. All right, the measurements are complete. We can see them appearing on our table, a bone volume fraction of 0.38. We can see the average trabecular thickness is computed to be 140 microns. Once you have measurements in this table, you can click the Export to CSV if you want to put them in a comma-separated values table that can be accessed by other tools offline, such as Microsoft Excel or other spreadsheet readers. What we've done to this point is we've done a binary segmentation of our bird humerus, and then we capped it, and then we pushed it through the cortical trabecular separation so that we could make microarchitecture measurements. Now these are global microarchitecture measurements that we've made, and we've only done BVTV and trabecular thickness. You can also make 3D mappings, which will be the subject of another video. You can also make axial measurements, so if you wanted to measure BVTV per slice or you wanted to measure cortical thickness per slice. You also have measurements like moments of inertia per slice, endocortical surface, or endocortical perimeter and periosteal perimeter. So I mentioned all of those now, but we will reserve that for a separate video. So in this video, we've looked at making the cortical trabecular separation and then these global measurements. I do want to take the trabecular thickness one step further though. Since we have computed a trabecular bone segmentation, if I hide everything except the trabecular bone, one of the things that we can do here is we could ask for a visual representation of the trabecular thickness in different areas of the bone. In order to make the compute time reasonable, what I'm going to do is I'm just going to select this region of interest. I'm going to click the B button to turn on the clipping box, and I'll look at the clipping box in a few different views. Drag the crosshairs down here, and we're just going to select a small region. Okay, and we can also make the adjustments in the 3D view if we want. So I can zoom out and say, let's make this a little smaller and maybe tuck it in a little bit from this view, etc. Now with that in place, I can right click on a region of interest and ask for a crop and create a new data set. So this is just a subvolume of the trabecular bone. And I'll go ahead and turn off the clip box there. So with this region of interest, whether we've made it with bone analysis or any other tools, all of the regions of interest inside Dragonfly, you can always select them, and on the segment tab in the ROI tools panel you will find the export to thickness mesh option. So we're going to ask it to create a thickness mesh with some smoothing, and the result is going to be a new surface mesh that shows just the trabecular bone in that clip box that we drew. And it's going to be a surface mesh that colors the trabecular bone based on the local thickness. So it'll give us a visual representation of how the trabecular thickness varies over the area. So it'll tell us a little bit about the variance, and it'll tell us about the local thickness in a nice color-coded rendering. So we'll give that a few minutes for the mesh to compute. The computation is now done. It's made the mesh and it's encoded the thicknesses on it, and it has performed a round of smoothing on the mesh. So if I turn off my micro CT scan rendering and I turn on the thickness mesh, then we'll see it appear in the 3D viewer. And there it is. And so what we're looking at is the trabecular bone in that region, color-coded by thickness. Now it's color-coded by this rendering, this lookup table. I'm going to right-click on the thickness mesh and choose the measurement inspector. And I have this measurement inspector. I'm actually going to undock it and move it over here. This allows me to see the histogram of thicknesses that are actually measured, and it also allows me to to change the lookup table. I'm going to choose the jet lookup table. And this allows me to quickly see the areas that have very high thickness and the areas that have very low thickness. Right now, thickness is mapped based on this data set where the smallest thicknesses in here are on the order of 60 microns and the largest thicknesses are about 400 microns. If you want to put it on a fixed scale so that you can compare it to other maps, we could set it to go from 0 to 500, for example, and now everything's colored on that scale. One of the nice features of the measurement inspector is you can modulate the rendering of what is selected in the case of measurement meshes like a thickness mesh or even multi-roys. Now what I mean by modulate the rendering is you get to select a window here and you can choose the opacity for what's in the window and what's out of the window. So if I say everything that's out of the window should have maybe 20% opacity, then you can see that I can set it so that I have full opacity only on the thicker parts of the mesh. I could even take everything that's outside the window, so that's everything here, and drop its opacity all the way to 0. And so now we're looking at just the thickest parts of the trabecular mesh. So these are where the struts cross or where the struts are just slightly thicker than other areas. So this gives us a way of sort of filtering out the tiny little bits. So if we don't want to see any of these little bits, then they end up getting filtered out. So this gives us a nice rendering of what the trabecular lattice looks like and how thick it is. And so again, it's being mapped from 0 to 500 microns thickness. So that gives you a nice idea of some of the measurements you can make in Dragonfly, some of the global measurements like BVTV and trabecular thickness, but also the ability to have these renderings so you can look at the trabecular thickness as a surface mesh, so you can have some localized viewings of those different properties. So that concludes all the material for this tutorial. I want to apologize. I should have at the beginning of the video thanked Dr. Natalie Resnikov, who prepared the material for this particular tutorial. So this gives you an introduction of the bone analysis extension as applied in this case to a bird humerus micro CT scan. So you see how you can compute microarchitecture measurements. So please look out for the other bone analysis videos. You'll see one that extends the discussion on cortical trabecular separation, another one on computing axial measurements as compared to the global measurements, another one on anisotropy, and another on 3D mapping. So thank you for your attention, and we hope you enjoy the bone analysis extension and hope you enjoy Dragonfly.